Welcome everyone, my name is Thijs Vlucht. Today I will discuss with you some of the basic aspects of heat pumps. The learning objectives of this lecture are: first, a brief recap on what is heat; second, what is a heat pump; third, a description of the vapor compression refrigeration cycle, which is one of the most common thermodynamic cycles for heat pumps; and four, something about the thermodynamic efficiency of a heat pump; and five, finally, an exercise. A lot of background information on heat pumps and refrigeration systems can be found in the excellent textbooks by Moran and Shapiro, Principles of Engineering Thermodynamics, Infante Ferreira and Kiss, Heat Pumps in Chemical Process Industry, and Dinser, Refrigeration Systems and Applications. Heat is energy that flows naturally from a high temperature to a low temperature, and the resulting heat flux is due to a gradient or difference in temperature. Heat always flows from hot to cold, unless we do something extra, as we will see later. Suppose that we would like to use electricity, convert electricity into heat, for example in an electric heater to heat a room. We can do this with a thermodynamic efficiency of 100%. So 1 kilowatt of electricity leads to 1 kilowatt of heat. But with heat pumps we can do much better than this. A heat pump is a device that transforms heat or energy from a low temperature reservoir, the cold body, to a high temperature reservoir, the hot body, which is exactly opposite of the normal flow of heat. Making heat flow from cold to hot requires mechanical work. This is shown in the figure on the left. An amount of heat Q in is removed from the cold body and the heat term Q out is transferred to the hot body. The first law of thermodynamics, which is essentially the conservation of energy, tells us that energy cannot be destroyed. So applied to this situation, this leads to an expression for the required mechanical work. The work of the cycle equals Q out minus Q in. The so-called coefficient of performance is defined as the useful effect divided by the amount of input required to obtain this effect, which is here the amount of mechanical work needed. Depending on what is the useful effect, either heating in a heat pump or cooling in a refrigerator, the definition of the COP, the coefficient of performance, is slightly different. COP equals Q in divided by the work of the cycle for a refrigerator, and COP equals Q out divided by W cycle for a heat pump. We will see that the COP is usually larger than 1, which makes a heat pump more efficient than direct electrical heating, which has a COP of 1 by definition. A popular and simple thermodynamic cycle for heating and cooling is the so-called vapor compression refrigeration cycle. In this cycle, a working fluid or refrigerant is undergoing expansion and compression, and the working fluid is both evaporating and condensing. Let us look in detail at the cycle and the corresponding temperature entropy TS diagram. At point 1, the working fluid is a saturated vapor. The working fluid is compressed, preferably adiabatic and reversible, so this means isentropic, to a state 2S. This compression requires mechanical work. If the compression is isentropic, the line connecting 1 and 2S is vertical as the entropy is constant and the temperature increases according to the first law of thermodynamics. At point 2S, the working fluid is entering a condenser, which means that the heat released to a high temperature reservoir, and due to the heat transfer from the working fluid to the condenser, the working fluid is condensing to a liquid. We assume that the pressure is constant in the condenser, no pressure losses due to friction. If the working fluid is a pure component system, then the temperature of the working fluid will stay constant during the phase transition. Entropy is decreasing as the entropy of the liquid is much smaller than that of the vapor. At point 3, all the working fluid is condensed and we have a saturated liquid. Next, the working fluid is entering an expansion valve or throttle, which reduces the pressure of the working fluid. At stage 4, the working fluid exits the valve. As the enthalpy difference over the valve is 0, this follows from the first law of thermodynamics, due to the Joule-Thomson effect, part of the fluid will evaporate, so point 4 will be inside the vapor-liquid phase envelope of the phase diagram. In the evaporator, heat is taken from the cold body, which results in the full evaporation of the working fluid in the state point 1, and the entropy increases again. For a pure component working fluid, the temperature stays constant during the vapor-liquid phase transition. We assume that there are no pressure losses inside the evaporator, just as for the condenser. The net effect of this cycle is that heat is transferred from a low temperature body, due to evaporation, to a high temperature body, due to condensation. What is needed as input is the mechanical work of the compressor. In case of heating, the COP of a vapor compression refrigeration cycle is defined as COP equals Q out divided by the work of the compressor. From the second law of thermodynamics, we can show that the maximum possible efficiency of this cycle only depends on the temperatures of the reservoirs in Kelvin, and that this equals to COP max equals Q out divided by Q out minus Q in equals T hot divided by T hot minus T cold. Please note that the temperatures T in this equation are in Kelvin and not in Celsius or Fahrenheit. This is the so-called Carnot efficiency, and we are unable to do any better than this. The so-called second law efficiency, or Carnot efficiency, is defined as the actual COP divided by the COP of the corresponding Carnot process, and the second law efficiency is always smaller than 1. In fact, given the temperatures of the hot body and the cold body, you can calculate for a given process how well it performs compared to Carnot. For a cooling cycle, the COP is defined slightly different, as the usual effect is heating instead of cooling. COP equals Q in divided by the work of the compressor. The maximum COP is given by Q max equals Q in divided by Q out minus Q in, and this equals T cold divided by T hot minus T cold. Now you have enough background for a small exercise. A heat pump cycle is used to maintain the interior of a building at 20 degrees Celsius. The heat pump receives energy by heat transfer from well water at 10 degrees Celsius and discharges energy by heat transfer to a building at a rate of 120 megajoule per hour. Over a period of 14 days, the electricity meter records that 1490 kilowatt hour of electricity is provided to the heat pump. You are asked to determine the coefficient of performance of the heat pump. The first step is to calculate the mechanical work. The work of the compressor is 1490 kilowatt hour, and this corresponds to 5.364 times 10 to the power 6 kilojoule. And the total energy transferred to the hot body. This is Q hot equals 120 megajoule per hour, and this in the end leads to 40.32 times 10 to the power 6 kilojoule. From the conservation of energy, we find the heat that is transferred from the cold body. Q cold equals Q hot minus the work of the compressor, and this is equal to 34.96 times 10 to the power 6 kilojoule. Then we can calculate the COP. The COP is Q hot divided by the work of the compressor, and this is then 7.52. The maximum COP is the Carnot COP, and this follows directly from the temperatures of the hot and the cold bodies. COP max equals T hot divided by T hot minus T cold, and this equals to 29.3. By dividing the COP with the Carnot COP, we finally find the second law of efficiency, 7.52 divided by 29.3, and this is 0.26, which means 26%. This means that there is some room for improvement in the COP of this heat pump. To summarize our learnings, we have learned that a heat pump transforms heat from a low temperature to a high temperature against the flow of normal heat. This requires mechanical work. The work of the cycle equals Q out minus Q in. The COP of a heat pump is the ratio of the heating output to the energy input to run the machine. Higher COPs equate to higher efficiencies, lower energy or power consumption, and thus lower operating cost. Thank you so much for your attention.